Alright, so here we go with the second half of the lesson for the inverse of a quadratic function. Just restating our learning goals, success criteria, and practice questions. We're going to be moving on, starting off with example number 3. And so with example number 3, we are told to use a graphing calculator to graph f at x is equal to negative 2x plus 1 squared plus 4 and its inverse. And so in light of this asking you to use a graphing calculator, all that I'm going to be taking us through in this case is getting the inverse, okay? I expect that you will be using Desmos, and you should go in there and plot f at x using y equals negative 2 times x plus 1 squared plus 4. Alright, so when you do graph it, I'm hoping that everyone notices that you should have a vertex found at negative 1 and positive 4, and that this is going to open down and be stretched by a factor of 2. Moving forward, the textbook actually goes through and does a solution for how to get the inverse. So we would be using the exact same method. You'll start out by first replacing x and y with each other, and then you're going to go about isolating for y. So we'll go through our steps. First, we're going to deal with that plus 4. We're going to subtract it from both sides, as we see here. Next, we're going to divide both sides by negative 2, seen right here. We're then going to address the exponent of 2 by taking plus or minus the square root on both sides. Now, this is what I'm really concerned with because we still see plus or minus. Now, in this question, it doesn't ask you to do anything in terms of the inverse of f at x as an equation. It just wants you to use a graphing calculator to graph it. So the reason that I'm spending some time highlighting some things in this inverse is that we need to be able to graph both the positive root and the negative root in order to get the actual graph of the inverse. So when we do that, we're going to have to actually input two separate equations. We're going to say that y is equal to the root of x minus 4 over negative 2 minus 1, and we're going to say y is equal to the negative root of x minus 4 over negative 2 minus 1. Doing so is going to allow us to actually get both arms, because if we have a Cartesian plane, our first equation here, y equals the root of x minus 4 over negative 2 minus 1, will just give us the first arm. So we're going to see it starting at 4 and negative 1, so somewhere along the lines of right here, and it will open back. Our second equation here will also start at 4 and negative 1, but it is the negative root, so it's going to be the arm that opens downward. So once you've gone through and graphed in Desmos, you should be seeing a more accurate depiction of these two arms, both opening from a vertex value of 4 and negative 1, and traveling to the left. Our last example is a word problem. This is example number 4, directly from chapter 3.3, and it says, the rate of change in the surface area of a cell culture can be modeled by the function s at t is equal to negative 0.005 times t minus 6 squared plus 0.18, where s at t is the rate of change in the surface area in square millimeters per hour at a time t in hours. And we're also told that 0 is less than or equal to t, which is less than or equal to 12. Pay no mind to my bad less than or equal to's. I don't know how to code for that in this software yet. We're asked to do three things here. First, we will state the domain and range for s at t. Then we will determine the model that determines the time in terms of the surface area. We'll address that in more detail later. C asks us to determine the domain and range of this new model. So we're going to start out just taking a look at part A, state the domain and range for s at t, and there's some critical information given to us right there. So we're going to be putting that to use. Now, if we look at our equation, we can see that s at t is a quadratic equation. It's going to open down. We're going to have a vertex at 6 and 0.18, and we will see that this function only exists from 0 to 12 hours. So, putting that all into context, it is a quadratic. So, for the domain, we know without a doubt that x will be an element of the real number system. Looking at the fact that t, our independent variable, is our time in hours, and that 0 is less than or equal to t, which is less than or equal to 12, we can use that as our condition. 0 is less than or equal to t, which is less than or equal to 12. And what this means is that our function is only going to be existing from 0 to 12 hours. We have no domain before 0 and no domain after 12 hours. So in the context of like this experiment, we're growing a bacterial culture, and it starts out not occupying any space, but then as we run this experiment, it will peak at 6 hours, meaning the culture will be its largest in surface area at 6 hours, and after 6 hours it will slowly begin to decline again. Okay, this is common when cultures use up all their food source, so the bacteria keep growing and growing and growing, and after 6 hours they've reached their maximum surface area, and then all of the bacteria start to die off because their resources are running out. Okay, so with that context, we now need to figure out what our actual range is going to be. So our range here is also coming from a quadratic function, so y would be an element of the real number systems. And we are now needing to figure out what our maximum and minimum values are. So our surface area here, we know, is going to peak at its vertex. So it's actually easiest to do the greatest value, which in this case comes from the vertex, so it's 0.18. The smallest amount is the limit on the surface area. Now for us, that would be 0 because you can't have a negative surface area. So 0 is less than or equal to. And I am noticing now, please bear in mind that I've used x and y here. I should actually be saying t is an element of the real number systems and s is an element of the real number systems. Alright, so for part B, things are a little tricky. We need to pay attention to the way this question is worded, and the way it's worded is to determine the model that determines the time in terms of surface area. So this is a little different than me just asking you to find the vertex, because I want you to find t equals, okay, but t in terms of its surface area. So if you follow along in the textbook, you would have noticed that it starts out with the surface area being equal to negative 0.005 multiplied by t minus 6 squared plus 0.18. So there's our original equation, okay? And so what we're going to do is solve for t, okay, but we weren't told to find the inverse. So we're not actually going to relocate s and t. We're just going to isolate for t. Okay, and that comes from this right here. determine the time in terms of the surface area. All right, this is no different than if I were to give you y equals mx plus b and say, rewrite the equation in terms of x. Okay, so moving forward, we're going to start our isolation process. We're going to start by bringing that 0.18 over, so we're going to see s minus 0.18 being equal to negative 0.005 multiplied by t minus 6 squared. We're going to divide here, so that's going to become our denominator. So divided by negative 0.005, and we've got a root there, so let's take the square root of both of these. Alright, what that's going to mean is we will see that the plus or minus root of s minus 0.18 over negative 0.005 is equal to t minus 6. Alright, so if that's the case, we're just going to add 6 to both of the sides here. So we have 6 plus or minus s, the root of s minus 0.18 divided by negative 0.05 is equal to t. Now that's a little bit messy, especially leaving that negative in the denominator, so let's rewrite it. T is going to be equal to 6 plus or minus the square root of negative s plus 0.18 divided by 0.005. Okay? And so what this does is it presents our function that originally told us the surface area at a given time, and now we're determining the time for an input surface area value. And last of all, we are asked to determine the domain and range of our new model. Well, our domain and range are still going to be based on the same limitations, meaning that we can't go into the negatives and that we have set maximums. The only difference is that they're found in the opposite location. So our domain was time, but now our input value is s, or surface area, so our domain must reflect the surface area. So our surface area is an element of the real number systems, such that our lowest surface area is still going to be 0 square millimeters, and our maximum surface area is still going to be 0.18 square millimeters. Our range is our time. So, just as before, time is an element of the real number system, such that 0 hours is less than or equal to the time, which is less than or equal to 12 hours. So as we see, our domain and range still present like they would in the case of the inverse. Okay, and we're still using an inverse process here. It's just that we didn't search out the inverse function. We searched out the original function to be expressed in terms of time. And I know that that gives people some trouble, okay? But you have to reason it out. You didn't take the inverse, but rather you reallocated your focus. You're now searching for time from a given surface area, okay? If you have questions about this one, feel free to email me. I know that it gave problems to some people over the last couple weeks, so any further clarification needed, just reach out, okay? And that concludes our first lesson for learning at home. So we've gone through the inverse of a quadratic function. We took a look at the fact that the inverse of the original function undoes what the original function has done. It can be used to determine which values of the original dependent variable produce the given values for the original independent variable. The inverse of a quadratic function is not a function. We must restrict the domain of f at x for the inverse to be a function, and we saw that clarified in example number 2. Our success criteria is to determine the inverse of quadratic functions, and we've gone through various strategies to allow us to do that, be it using the graph or using the equation. Moving on, your practice is going to come from chapter 3.3, and you're looking at questions 2 through 12. As in every case, you don't have to do every single question. You should be allocating as much time as necessary. So if you're flying through this stuff, feel free to skip questions. If you're having a lot of difficulty, you should email me about the problems you're having, and then once we've had a chance to resolve those, you should be trying to work through the rest of the questions. All right, have a good day, everyone. We're going to have another lesson posted for Thursday of this week, and Wednesday is going to be treated kind of like an office hours time. So if you're having trouble, we can dedicate all the time during the day towards answering any questions. All right, we'll see you again later. Bye.